So let's say you're working through your first year coursework and you encounter an integral like this. I'm going to discuss 1, where might we find integrals that we can use our complex analysis tools for? 2, if we saw this, how would we know that this might be a good candidate to use complex analysis on? And then we're going to work through it, go through all the numerics, find the residue, and evaluate this integral. So, complex analysis can be used lots of places, but typically it'll show up when you're doing linear response theory, when you're using the Kramers-Kronig relations, anytime you're doing dissipation fluctuation, or generally anytime you have closed loop integrals, anytime you have things with just functions of r and theta, the things that parameterize our complex values, or anytime you see a function that has poles or points in the denominator where your function will blow up. All of these are hints that we might want to try using our complex analysis toolkit to solve these integrals. So, this specific integral, we see we are integrating over theta from 0 to 2 pi. Theta goes in a circle as it travels through these values from 0 to 2 pi. This will be a closed loop integral, right? We are starting at one point of theta. As we integrate through this path, we end up back at our original point. So, this is not a complex valued function, right? Theta is not going to have a complex component. So the first step of what we have to do is we have to make substitutions so that this is a function of z. And it's going to be useful to use our definition of z equals r e to the I theta. One thing you'll notice, this function does not have any r's inside of it. And so we can choose to plug in a value of z where r is fixed at 1. This is just going to simplify our math, and we'll see that we should still be able to make all the substitutions we need even if we don't leave this as a general value. So if we do that and we plug this in, we have to figure out some way to equate these things. So if we use properties of e to the I theta and cosine, we can rewrite cosine theta as e to the I theta plus e to the minus I theta over 2. This comes from, if you take the Taylor expansion of cosine theta and e to the I theta and e to the minus I theta, you'll see that if you add these two series and divide by 2, you end up getting the same series that you get for cosine theta. So, now that it's in this form, it's looking a lot more like our complex variable z, right? We need to replace this theta and this theta with our function z. So, if we do that, here, e to the I theta is equal to z. E to the minus I theta, we could write in one of two ways. We could write this as the complex conjugate of z, but that's not something we like to do, right? Remember when we were talking about the definitions of our complex functions, we said that if we wanted our function to be holomorphic, it needs to be a function of z only, not z and some complex conjugate. And so we could rewrite this instead as 1 over z, the inverse of z, right? This is the same as 1 over e to the I theta. And so we'll write this as 1 over z. This over 2 sticks around, and we figured out a way to sub in for cosine theta in just our complex variable. Now, something else we have to worry about is this d theta, and so we have to take our complex number and find out how to turn it into a dz. So if we differentiate both sides, we will get an I d theta, e to the I theta, and e to the I theta is just z, so this equals I z d theta, or in other words, d theta is equal to dz over iz. So these are all the substitutions we need. We can then take all of this and plug it into our integral. And now we can rewrite our integral as something that we can do complex analysis on. So I'll write what's the integrand first, then we'll worry about the limits. So we will have a dz. I'm going to move this iz to the denominator. I'm actually going to pull the I outside. I think that'll make it a little clearer what's happening inside. So we have a z. Then we have this, which we've transformed to be 5 plus 4. And I'm going to pull the 2 out. 4 over 2 times z plus 1 over z. So what are the limits of z? We said that we had theta going from 0 to 2 pi. And so that is equal to a circle in our complex space with a fixed radius. So it's good that we fix the radius. It means we have a circle where the absolute value of z is equal to 1. So this is a closed loop integral along a contour. Okay, so we'll plot this in just a moment, but we do need to simplify this ugly form down here. You can work through the algebra at your own speed, but this will end up simplifying to 1 over I integral of dz. If you distribute this, you divide the 4 by 2, you distribute the z, you end up getting 5z plus 4z squared plus 2z squared plus 2 and if we end up factoring this into something that is not a polynomial but a product of binomials, then we would end up turning this into, I'll write it up here in the form that's useful to us, the integral over c dz over 2z plus 1 times z plus 2. So we factored this, and so that will help us evaluate what is going on here. So we have some integral. We're taking the integral of a function of z, and so this satisfies all the requirements for our complex analysis tools. So if you remember from the last video, we had Cauchy's theorem, which said the closed loop integral is 0 if our function is analytic everywhere inside of this circle. But we have some values of z which will give us poles. So we need to figure out where these poles are. And those are just the values of z that make this function blow up. So our f of z, just to write it out for clarity, is 1 over, I'll factor a 2 out of here just to make things a little bit more consistent with the form that we've seen it before, z plus 1/2 times z plus 2. All right. So if we are looking for the poles, we can identify the poles are at z equals minus 1/2 and minus 2. Okay, so we have 2 points in complex space where our function blows up. Let's plot this. Real axis, imaginary axis. Our contour, we said, was a fixed value of z equals 1. So that's z equals 1. That is our contour C. Our poles are both real numbers. So one of them will be at minus 1/2 right here. One of them is at minus 2. So we see even though we have two poles, only one of them is inside our contour. So that's going to be important, right? If you remember the residue theorem from last time, we said that if we wanted to evaluate this integral, our integrals will be equal to our closed loop integral over a contour of f of z dz is equal to 2 pi I times the sum of the residues in our contour. So this is the definition of residue theorem. If we look at our system, we have f of z, right? That's just basically 1 over this stuff. We have a pole inside of our circle. It is a simple pole, right? If we plug in minus 1/2, there's no exponent here. This is just going to be a simple pole, order 1. And so if we can find the residue of our function at this point, then we are going to be able to calculate this right-hand side. And by mapping this out, we see we don't have to worry about this pole. It's not in our contour. It won't contribute to the value of the integral. So to find the residue of this point, we take f of z and we multiply times z minus z naught, or the point of interest where we're trying to calculate the residue. It's important that we plug it in like this, z minus some value. We can't just multiply f of z times the whole term that gives us the singularity, because by expanding our function in terms of the Laurent series, we're not going to have a term with a 2z. We only have terms of z minus z naught. So if I simplify this real quick, that'll just be z plus 1/2. And so we take this, we multiply times z plus 1/2, and we evaluate it at z equals minus 1/2. So our function f of z times z plus 1/2 is just going to be 1 over 2 z plus 1/2 times z plus 2. This is f of z that I've written down so far. We multiply times z plus 1/2. This term cancels with the term that gives us the singularity when we evaluate at z equals minus 1/2. And so all that's left is we plug in z equals minus 1/2 here, and we get the value of our residue. Minus 1/2 plus 2 will be 3/2. We multiply that times 2, and we get 3. So this works out to 1 over 3. The residue of z equals minus 1/2 is 1/3. And so we're able to solve this integral, 1 over I times this closed loop integral, because we know that this integral evaluates to 2 pi I times the sum of all the residues, which is just 1/3. So I, our big integral from before, is equal to 1 over I times 2 pi I times the sum of the residues, which is 1/3. And if we multiply this all out, the i's cancel. 2 pi divided by 3 is our answer. So I'm not going to say that there's not other ways to evaluate this integral. Perhaps you could find some clever u sub, or you could do something else. But there's a very straightforward path to evaluate it using our complex analysis tools. One other thing to mention, when we found our contour, we found that only one of our poles was inside the contour. Did that just happen because I said, hey, let's use z equals 1? What happens if I used z equals 5 e to the I theta? Would we then draw a bigger circle where this pole's inside? Would that change our results? Well, it turns out if I plug in z with some other fixed radius, the locations of the poles will still be the same relative to our contour. When you plug everything in and you find the poles will no longer be at exactly these same locations if we use a different contour, but we will still have one of them inside, one of them outside. We're mapping this function to complex space. And so the poles that are encoded within this function will also map to the same relative places, i.e. inside the contour for this one, and the other one will be outside the contour.